Okay, so our next speaker is Patrick Wynne, and he'll tell us about clonoids.
Thank you. Yeah, thanks for the opportunity to speak today. So, yeah, I want to discuss clonoids, and specifically, I want to talk about clonoids between finite modules. So first, what is a clonoid? A clonoid is a set of functions from powers of one algebraic structure into a second algebraic structure, which is closed with respect to the operations of each structure, essentially. So a clonoid is first closed with respect to, so if we have a clonoid from A to B, then first we're closed with respect to the term functions of the algebra A. So clo A here just represents the term clone of A. And also our set of functions is closed with respect to the term clone of this image algebra of B. And so what does that mean? We can essentially act by operations of A, then map and act by operations of B, and this new function that we obtain should still be within our clonoid. So this is sort of the closure property that we're after. And so just a nice, easy little example. If we take A to be an abelian group and B to be a lattice, then if we take some functions f and g, then we can form a new function h, which takes f and adds two variables, x1 plus x2, and g, we have x1 plus x2 in the first coordinate, which is a term function, and then another term function, x1 plus x3 in the second coordinate. And now we can take the mean of these two new functions. Now we have a new function, which still should remain in our clonoid. So closed on the, with respect to the operations of the first algebra and the operations of the second algebra. And so for a pair of relations R and S in powers of A and B respectively, say nth powers, then the set of polymorphisms of this relational pair is all the functions that preserve this relational pair. So if we have some function f, it preserves the pair RS if we take tuples from R in each coordinate and act coordinate wise, we should get a tuple from S. And so a theorem from Cusero and Foldish says that if we have R and S actually are subalgebras of powers of A and B respectively, then the set of polymorphisms is actually a clonoid from A to B. And so another little example, let's take A to be the integers mod p squared with addition and B to be the integers mod q with addition as well. Then if we look at the relational pair equality mod p and equality, then the polymorphisms that preserve this relational pair are exactly those functions that are constant on classes modulo p. So if we take some pair that's equivalent mod p here in each coordinate, then we map coordinate wise, then we should get some pair here that is equal. Okay, so the question I want to talk about is for a given pair of structures A and B, in particular for a given pair of modules, how many clonoids from A to B are there? And so first, a theorem from Erhard Eichinger and Peter Meyer, and I should mention this is all joint work with Peter Meyer. We get that all of these clonoids from A to B, at least when B is a finite Maltsev algebra, then the set of clonoids is actually finitely related. So there's a finite set of relational pairs that determine the clonoids. And so this gives us then an upper bound on the number of clonoids from an algebra A into a Maltsev algebra B. And so this is a countable upper bound. We can actually weaken this a little bit. We don't really need a Maltsev term in the algebra, but we need some edge term. So if the algebra B has an edge term, which a Maltsev term is an example of an edge term, then we get this result as well. We can do a little better than this. And why study clonoids? So the motivation for, at least why I started looking at clonoids, was I was studying nilpotent algebras. And so essentially, clonoids arise in the study of nilpotent algebras. If from the book of Friese and Mackenzie, we have that if we have some algebra that is nilpotent, then it's essentially, say, nilpotent of degree n. It somehow looks like a nilpotent algebra of nilpotence degree n minus 1. And abelian algebra or algebra of nilpotence degree 1 somehow twisted together, and somehow the clonoids arise when studying this. I won't go into any more details than that for now, but so they sort of arise naturally in a few different instances. We also saw an instance from Peter's talk earlier today where clonoids came up again. So yeah, I won't motivate them, and I'll just talk about them. So the problem is, given two finite modules A and B, can we classify the clonoids from A to B, or maybe less ambitiously, can we at least say how many clonoids are there from A to B? And so Sebastian Kreiniker showed that for an odd prime P, the number of clonoids from integers mod P to the integers mod P is actually countably infinite. And he characterized them fully. There's the finitely generated ones, and then there's also countably many that are not finitely generated. And so first we'll generalize this a little bit. So we have algebras A and B, or modules A and B rather, which are not of coprime order. Then in fact there are still countably infinitely many clonoids from A into B. And so the proof idea is essentially the first step is to essentially reduce down to just the integers mod P, the nth power, acted on by the matrices. So the full matrix ring here, and then the same thing for B. We have a full matrix ring, but maybe some different size. So let's see. So yeah. So the idea is I'm just going to construct a chain of infinitely many clonoids, an increasing chain. And so the first step is if we take a tuple x1 through xn from A. I'm going to map it to just essentially I'm just going to truncate it if m is too short, and I'm just going to pad it with zeros if m is too big. And now I'll just define the binary multiplication, just the normal multiplication on ZP in each component. So now we have a binary function from A into A, which just multiplies in each component. And then if I combine these together, so this here I just mean the iterated multiplication in ZP. So first we multiply term by term, k many copies of these tuples from ZP to the n, and then truncate or pad with zeros if we need to. Maybe it's easiest just to think if m and n are equal, we just multiply component wise. Okay, so now I claim that these f's, f1, f2, f3, etc., they form an increasing chain of clonoids. So the way to see this is that fk is zero absorbing. And by zero absorbing, I mean that whenever one of the x's is zero, then the output is zero. So just going back to the definition, this is pretty clear because it's defined just by the multiplication in the integers mod p. So if we have the zero tuple as one of our inputs, then of course every tuple will be the zero tuple, and the whole product will be zero. And so the FKs are zero absorbing, and then we can see quite easily that actually the functions that we can construct from F1 through Fk of arity greater than K, say of arity K plus 1, all these functions are actually not zero absorbing. And this boils down to just using that the multiplication in the integers mod p and the addition behave well together. We can essentially distribute this multiplication across addition. But the function fk plus 1 actually is zero absorbing, and so that means that the clonoid generated by f1 up to fk doesn't produce any zero absorbing functions. And so if we toss in fk plus 1, now we have a strictly bigger clonoid. And so that shows us that this chain here is a strictly increasing chain of clonoids. And so there's for non-coprime modules A and B, we have countably many clonoids from A to B. So that gives us a lower bound, and we already had an upper bound from before. And so there's exactly countably infinitely many clonoids for non-coprime modules. And now the picture is a little bit different for when the modules are of coprime order. So Stefano Fioravanti showed that for distinct primes P and Q, the number of clonoids from ZP into ZQ is finite. And the way that he showed this was by showing that every clonoid from ZP into ZQ are generated by just their unary functions. So if we know what the unary part looks like, then we know what the higher arity parts look like as well. And so the basic idea of this proof is if we start with some arbitrary function from power of ZP into ZQ, then we can interpolate this function on lines through the origin, meaning we can find a function f sub v, which looks like f on the span of some vector v, and it looks like 0 everywhere else. And the important thing is that we can build this function up from the unary functions generated by f. So we start with some function f, we look at the unary functions it generates. From those functions, we can get this new function, f sub v. And now, if we make the small assumption that f is 0 at the origin, then f is just the sum of a bunch of these f sub v's. Just add them up for these distinct lines through the origin, and then we recover f. So we started with f, we look at some unary functions, and then we can build back to f. And so every clonoid then from ZP to ZQ is generated by just its unary functions. And so in particular, of course, there's finitely many. And so now we generalize this result a little bit as well. And so the question we answered was, at least in the case for modules over commutative rings, exactly when does this happen that the unary functions generate the entire clonoid? And so that's what this theorem answers. And the answer is that every clonoid from A to B is generated by its unary functions is equivalent to that the two clonoids are of coprime order. That's what we already saw we needed. And that R is a direct product of finite fields. So the ring is direct product of finite fields, and then the algebra is the regular module over that ring. And so just a sketch of this proof. So to show that 2 implies 1 is essentially the same as the previous argument on the last slide. We're just going to interpolate some function by cyclic submodules of A to the K. So it gets a little uglier when we have product of finite fields here, but essentially the argument is somehow the same. And now in the other direction, if A is first, if A is generated by more than one element, say A is generated by K elements, then we can actually find clonoids that agree on their unary part, but disagree on their K-ary part. So in particular, for say A is generated by K elements for K greater than 1, then we have some clonoid that's 0 on its unary part, 0 on its binary part, all the way up to its K minus 1 ary part, it's 0. And then on the K-ary part of the clonoid, it's now non-zero. And of course, this is different than the clonoid of all just 0 functions. And so therefore, such clonoids cannot be generated by their less than K-ary part. So the first reduction is that A has to be cyclic. And since R is commutative, we just get that A is essentially R mod the annihilator. So now if the Jacobson radical of the ring is non-zero, then again we can construct clonoids that agree on their unary part, but now on their binary part they disagree again. And so in particular, that means that even for the regular module R sub R here, we get that the clonoids cannot be generated by their unary functions. So then we reduce to the case where the Jacobson radical is 0. We're working with finite modules here, so we don't have to worry about Artinian or Noetherianness or anything. We get that all for free. And so we get that R has to be semi-simple and it's commutative, so therefore it's just a product of finite fields. And then the algebra A is just the regular module over this product of finite fields. So this answers then the question, when is a unary generation enough for clonoids, at least in the commutative ring case? And so there's the answer. Of course, maybe we don't have finite generation for a clonoid, but maybe we still, maybe we don't have unary generation for some clonoid, but maybe we still have say binary generation or something like this outside of this setting. And so we'll look at that as well. So the question we answered as well is that if we have a prime P, then the integers mod P squared with addition as our source of our clonoid, and any non-trivial group as the image of our clonoid, then we have distinct clonoids with the same unary part, but distinct binary parts. So it's just an example of essentially illustrating that the last theorem, we push it sort of as far as we can. So here, this doesn't fall into our framework. We have the integers mod p squared, which is not a field. And so here's just an example of a pair of clonoids that agree on their unary part and disagree on their binary part. So for one clonoid, let's take the clonoid of all functions that are constant on these line segments defined like this: x plus r times p of x, where r ranges from 0 to p minus 1, and is 0 on p times zp squared to the k. And then D is the clonoid of all functions that are constant modulo p, so satisfying f of x equals f of x plus p times a to the k. So let's see. So here's the picture. So on the one hand, this is the binary picture for p equals 2 case. So the prime is 2. So we're looking at the integers mod 4. Then these line segments all live in the same block modulo p, and but they are, the blocks modulo p are just disjoint unions of such line segments. And so on the one hand, we're looking at functions that take some arbitrary value here, and then some other arbitrary value here, and some other arbitrary value here. And then we just made the assumption that there's 0 here, just to simplify things. And on the other hand, we have a clonoid that takes some arbitrary value on each of these line segments. And so clearly their binary parts are not going to be the same, but their unary parts actually are the same. If we look at the unary picture, then we just essentially get one line segment here. And so these line segments exactly match up with the mod p blocks. When k equals 1 for higher arities, we get that these line segments are different from the mod p blocks. And so then these two clonoids are equal on their unary parts, but not equal on their binary parts. Okay, and then we don't have quite the full picture for arbitrary modules or even for arbitrary abelian groups of coprime order, but at least for this case of zp squared, if a is zp squared and b is some module of coprime order, then actually every clonoid from A to B is generated by its binary functions. And so this argument is a little more involved than the previous one, but somehow we can, again, from some arbitrary function f, we can reduce it down to its binary functions, and then from these binary functions, again, build back up to f by interpolating not just on cyclic submodules, but on some more complicated substructures, and we can eventually build back up to f. And so then in that case as well, then for the integers mod p squared as our source of the clonoid, then we again get that there's just finitely many clonoids, because of course there's just finitely many binary functions. So what would be nice to answer is for say abelian groups A and B of coprime order, is it true that there are just finitely many clonoids from A into B? So right now this sort of interpolation argument for zp squared doesn't generalize very nicely to even say zp cubed or something like this. So there's still some work to do there, but that would be ultimately a nice question that I'd like to answer. And better yet, I'd like to sort of get a handle on these clonoids, some classification of these clonoids. So yeah, that's all I have for today.
Thank you. We have plenty of time for questions. No?
So you said you got into this trying to study nilpotent algebras. If you were able to completely come up with the number of clonoids between modules, would that be good enough for answering your original interest in nilpotent, or would you need a full classification?
Well, so I guess it depends. I was purposely a little big, so not quite. So if I knew, for example, that there's finitely many clonoids from, say, some abelian group to some other abelian group, then I wouldn't necessarily know then that there's finitely many, say, nilpotent expansions of one of those abelian groups by the other one. So it's not quite, you can't quite just translate between nilpotent expansions and clonoids, but yeah, the connection is not quite as straightforward as that. yeah, but I guess it would help in still understanding the term clone of say a two nilpotent algebra. Somehow you can hopefully just understand the you can sort of split off the linear part and the sort of the clonoid part, this distortion from Friese and McKenzie description of nilpotent algebras.
Anyone else?
The term clone comes from clone, right?
Yeah, exactly. So yeah, clone is just a set that's a set of functions from a power of an algebra, from a power of a set into itself, which is closed under all the sort of compositions that would make sense and contains all the projections. So of course, here we're going from some set to a different set, so the projections doesn't really make sense, but it's sort of closed under any composition of functions that makes sense in that sense.
But the clones like have a structure that clones do, because you can compare clones.
Yeah, so the set for a fixed algebra A and B, the set of clonoids from A to B will form a lattice. And so I guess strictly speaking, from the way I originally defined them, I think maybe the empty set is the yeah, so I think then the empty set would be the smallest element of this lattice, and then the largest element would be the set of all functions from powers of A into B. And then the me would just be intersection, and the join, well, the join is very easy to describe, where in the case where B is say an abelian group or an expansion of an abelian group, the join is just looks like essentially functions from one clonoid plus functions from another clonoid with the same arity. So yeah, they have that nice lattice structure, but yeah, maybe not quite as nice as the structure.
I have the structure B if you fix it. You can think algebraic operations.
Yeah, so if we fix an arity, say, let's say we look at functions from say A squared into B, the set of functions from A squared into B, we can think about that as being an algebra of type, whatever the type of B is, say a modular, whatever.
So maybe just to add on to that, if you know clones, you know that there's a lot connection between clones and relational structures. Right? So using this polymorphism that I mentioned, and here for this clone, it's because domain and codomain are different. You also get a color connection, similar one, but you need pairs of relations to describe them.
Anyone online? For the question?
I want to ask something. I feel very arrogant doing this, but I don't completely understand the definition of clonoid, but it doesn't matter. What I'm seeing is that you're kind of counting powers of things and then take the union. And then you want to count the number of clonoids from one algebra to another. But in some of the results you mentioned explicitly that it is like an upper bound is countably infinite. Like, can you have finite models or algebras in which the number of clonoids are uncountable?
Yes, so not modules, but because of the result that you just mentioned. But yes, there are examples of. I think the easiest example is if you take, say, A to be just a 2-element set, and B to be a 2-element Boolean algebra, then there's actually uncountably many clonoids from A to B. And there's a paper from Athena Sparks, Peter's former PhD student, that answers this question of when is there uncountably many clonoids from A to B, and somehow it depends on trying to remember exactly how it goes. So her clonoids were slightly different. That A was just a set in that case, so no operations, but it depended on the structure of the. It depended on the term clone of B, whether or not there was some sort of terms. I think some near union in B term or something like this.
And in that direction, for example, what you're saying is that you can keep the continuum, right? As many
Yeah, you can hit the
clonoids as the continuum.
Yeah. So
For example, suppose that the continuum is Aleph 5. can you hit all the spectrum from ALE1, ALE2, with certain algebras or, you know?
Yeah, so I haven't thought about this, but so I don't have a great answer, but I think the answer is no. At least for finite A and B, where so I know the answer is no if A is just a set and B is some algebraic structure, finite algebraic structure again, then you'll either have countably many or continuum. I don't think you'll get anything in between. But yeah, I haven't really thought about that in general.
Okay, thanks a lot.